Let us move forward to the second module. First module focused on discrete Fourier transform, its theory and applications in the analysis of signals and systems, whereas the second module focuses on the structures for the realization of discrete time systems, especially the FIR and IIR systems. When compared to first module, second module is easy because it involves mostly of mechanical procedures. So in the syllabus, it is mentioned about FIR and IIR systems, but the third module is dedicated for FIR systems alone. For the time being, let us discuss only about the IIR systems in this second module. So let us see some of the useful terminologies associated with this module. A signal which is defined as anything which conveys useful information, and a system is a physical entity which performs operations on signal. And a discrete time system is a device or algorithm that operates on a discrete time signal to produce another discrete time signal. That is, in the case of a discrete time system, the input as well as the output is discrete time in nature. So in DSP, systems and filters are used synonymously. Hence, FIR and IR systems are actually FIR and IR filters itself. This system is a more general terminology compared to the filters. So in your fifth semester, you have studied about various types of classifications of signals and systems. Accordingly, say system can be classified as recursive and non-recursive systems. A recursive system is a system in which current output depends on previous outputs and inputs, but in non-recursive system, current output does not depend on previous outputs. Now, in the case of a recursive system, the output depends on output as well as the input. Now, in such a system is practically realized by providing a feedback from the output to the input. So in the case of non-recursive system, the output never depends on output itself, but it depends only on the inputs. Another classification is the FIR and IIR systems, which is based on the impulse response of the system. So as the name indicates, if the impulse response of a system is finite, then it is an FIR system, and if the impulse response is infinite, then it is called an infinite impulse response or an IIR system. So IIR systems can be realized in practice by recursive manner, that is by providing a feedback from the output to the input. So here are some of the symbols for the realization of structures for the discrete time systems. The first one is addition of two sequences, which is represented using such a symbol. Then multiplication by a constant is denoted using such a symbol, and in some certain textbooks we can see this type of symbol also. Now for unit delay, the symbol is like this one. So these are the three important symbols used in the realizing structures for the systems. Let us see the realization of some simple discrete time systems using the symbols. Consider an accumulator system. An accumulator system is whose output is the sum of the present and past inputs. That is, the output will be an accumulated sum of all the inputs, which can be mathematically represented using this expression. An accumulator system is given by y of n equal to sigma k equal to minus infinity to n x of k. Now put k equal to n, so that this expression will become x of n plus. Now the remaining terms are sigma k equal to minus infinity to n minus 1 x of k. Now what about the second term? So when compare this one, we can see the second term is actually y of n minus 1. So that we can rewrite this expression as x of n plus y of n minus n. So here you can see the output depends on the output. So the system is a recursive system. Now let us try to realize it recursively using the symbols. Here the x of n as the output, you can draw like this. Now the output y of n. So here we have x of n as the input and y of n as the output. Now we have the system equation as x of n plus y of n minus 1. So how can we get y of n minus 1? This can be easily achieved by providing a delay element. Now we can see the output of delay element will be y of n minus 1. Now we can simply sum the two terms so that the output will be like that. So this is the realization of an accumulator system using the symbols. This is the realization of an accumulator system. Another example is the first order constant coefficient difference equation, which is mathematically expressed as y of n equal to this one. Now let us see how this can be realized. Here we have the input x of n. Now let us begin with the input side. Now from the input side we can see b0 x of n plus b1 x of n minus 1. So here we have a delay element of x of n minus 1, which we can provide here. That is, we can provide a delay element here so that the output of the delay will be x of n minus 1. Now this x of n minus 1 is multiplied with a constant b1. Now we can see the x of n is multiplied with a constant b0, which we can provide here, that is multiplied with a constant. Now the sum of the two will give you the input side. So the intermediate result, the output of this one will be the b0 x1 plus b1 x of n minus 1. Similarly, we can go to the output side. We have the output y of n, and y of n is delayed by 1 unit, so which can be realized as the delay element, and the output of delay element is 1 y of n minus 1. Now this y of n minus 1 is multiplied with a constant, that constant is minus a1. Now the sum of the two, we will get the output side realization. Now we can see the sum of the two will give the final output equation. This is the realization of the first order system. Here we can see the correct picture of the first order system realized using the symbols. Another example is the realization of the second order difference equation given by the expression y of n equal to this one. Now this can be realized as our input side x of n. Now the input side x of n is multiplied with a constant b0, so we can provide a b0 here. Now in the output side we have, this is the output side y of n. Now we have a delay of 1, delay is the inverse n, and we know the output of the delay will be y of n minus 1, and which is multiplied with a constant a1. So this is multiplied with a constant a1. Then we have one more delay is there, which is related with the next delay. This is Z inverse, and whose output is y of n minus 2. Now y of n minus 2 is multiplied with another constant, which is a2. Now these two can be summed together. That is a1 of this one like that. So we can sum these two terms like this. So its output will be a1 y of n minus 1 plus a2 y of n minus 1. Now the resultant sum is obtained by summing the input and the output. Finally, we'll get the realization of the second order system. Here is the final result of the realization of second order system. So far we were discussing with the particular cases of realization of difference equations. Now let us generalize the realization of linear constant coefficient difference equation. The general expression for the linear constant coefficient difference equation is given by sigma k equal to 0 to n ak y of n minus k equal to sigma k equal to 0 to m bk x of n minus k. Now put k equal to 0 in this expression, we get a0 y of n plus sigma k equal to 1 to n ak y of n minus k, which is equal to sigma k equal to 0 to m bk x of n minus k. Now assume a0 equal to 1, or we are normalizing this expression with respect to a0 or dividing throughout with a0, so that a0 will be equal to 1, and the corresponding equation can be written as, we are taking the output term to the right side, we will get k equal to 1 to n ak y of n minus k plus sigma k equal to 0 to m bk x of n minus k. This is the generalized equation expressed in terms of y of n. Let us derive the system function from the general difference equation. A system function h of z is defined as the ratio of z transform of the output to the z transform of the input. The general difference equation we can write as y of n plus sigma k equal to 1 to n ak y of n minus k, which is equal to sigma k equal to 0 to m bk x of n minus k. Here we have taken the y terms to the left side and x terms to the right side. Now take z transform on both sides, so that we get y of z plus sigma k equal to 1 to n ak y of z into z raised to minus k, which is equal to sigma k equal to 0 to m bk x of z into z raised to minus k. So here we are applying the shifting property of the z transform so that we get the z raised to minus k. Now we can take y of z as the common factor so that the term will become 1 plus sigma k equal to 1 to n ak z raised to minus k, which is equal to sigma k equal to 0 to m bk x of z into z raised to minus k, from which the system function h of z can be obtained as y of z by x of z, which is equal to sigma k equal to 0 to m bk z raised to minus k all divided by 1 plus sigma k equal to 1 to n ak z raised to minus k. So this is the system function. The system function derivation is shown here. So this is the system function. Here we have the general difference equation and the corresponding system function. We can realize or implement these functions using various kinds of structures. The various forms of structures for realization are direct form 1 realization, direct form 2 realization, transposed direct form realization, cascade form realization, parallel form realization, lattice ladder structure, etc. In our syllabus we are dealing with all these structures. So why we are going for various forms of structures? Let us look into the reason for that one. There are mainly three major factors influence the choice of a specified realization. The three major factors are the computational complexity, memory requirements, and finite wavelength effect. What is computational complexity? It refers to the number of arithmetic operations, multiplications, divisions, and additions required to compute an output value y of n for a system. In addition to this, fetching time from memory and comparison between two numbers also come under this category. So while selecting a structure, we have to take into account the computational complexity of that particular filter. And the second one is the memory requirements. And our objective is to minimize the memory as minimum as possible. And the third factor is the finite wavelength effect. In digital domain, always we have registers with the finite length. So while assigning coefficients or values to a register, some of the values will be discarded or rounded or truncated. This will affect the performance of the filter which you have designed. So depending upon the requirement, we have to select which structures. In certain structures, the finite wavelength effect will be minimum. So that we have to take into account. In addition to this, the parallel processing and pipeline processing require other consideration. Because of these factors, we are selecting the structure for the best performance of this filter which we have designed. Now let us discuss with the direct form 1 realization of IIR systems. So as the name indicates, we are directly realizing the structures of the IIR system as per the general difference equation or the system function. So students should realize this system by a trial and error method by yourself. Then later you can recheck with the standard one. This is the standard structure of the direct form 1 realization. Now let us see how this is drawn in practice. For that, first you draw 6 adders side by side. Then connect it with the arrows. Then at a proper distance with the middle of the two adders, draw the delay. Similarly, at the left side, draw the delay. Similarly, here the just below and middle of the second adders, draw the delay lines. Then give the input x of n. Then the input is given to the first delay element. Then connect the input and output. Then connect the output. Then from the output, give the delays. Then from the middle to this one, draw one. Similarly, from the other side, draw this one. Then draw like this. Now we can give the extension like this and put arrow mark here. Then the same line just above, just below the adder, draw like this. Similarly at the other side, give the delay like this. Then now give the parameters x of n. Here we have the coefficient of x b0. Here it is b1, here it is b2, etc. Here it is bm minus 1, here it is bm. This a0, the a0 is always 1. And here you can see the arrow mark of a0 is to the right, whereas all other b's are towards the opposite direction, that is towards the left. So this is minus a1, this is minus a2, this is minus an minus 1, this is minus an. So this is the realization of the direct form 1 structure. You must draw the structure using a scale and pen or pencil and draw it neatly as shown in this standard form. Now we can do some problems based on the direct form standard structure. Say typical example. Obtain the direct form 1 realization for the system described by difference equation y of n, this one. As the first step, we have to write the given difference equation is y of n equal to this one. In its standard form, we know that we can put it as in this form. Now here we know that if you are taking the coefficients of y, that is a coefficients, then its negative will be the standard form. So ultimately what we are getting is the same coefficient. So we can directly write like that. The coefficient minus a1 equal to 0.5. Then here it is n minus 2. So the coefficient is minus a2 equal to minus 0.25. Then here b0 equal to 1. That is, the b's coefficients are corresponds to the x of n. Then b1 equal to 0.4. Now you look into this equation, the input side, that x of n plus 0.4, x of n minus 1. So input side we have a single delay element. So if a single delay element, you have to draw, first you draw two adders. Now in the output side you can see there are two delays. Then you have to draw three adders. So output side we have three adders. Then put the delay elements. Output side we have two delays. At the input side we have one delay. Then draw the arrow marks, the connecting arrow mark. We have the input x of n and output y of n, and the coefficients here are, this is b0. So b0 equal to 1 itself. Then b1 equal to 0.4. Then we have the coefficient minus a1 equal to 0.5. Then minus a2 equal to minus 0.25. So this is the realization of the given difference equation. This is the correct answer. You draw it neatly like this. Let us solve the same difference equation using the system function approach. For that, first you have to take Z transform on both the sides of the equation, so that y of z equal to 0.5, y of z is raised to minus 1 minus 0.25, y of z is raised to minus 2 plus x of z plus 0.4, x of z is raised to minus 1. Now take the y terms to the right side, so that we get y of z do 1 minus 0.5 z inverse plus 0.25 z raised to minus 2, which is equal to x of z do 1 plus 0.4 z raised to minus 1. Now the system function h of z can be obtained as y of z by x of z, which is equal to 1 plus 0.4 is raised to minus 1 divided by 1 minus 0.5 is raised to minus 1 plus 0.25 is raised to minus 2. Next step is to obtain the coefficients. So the denominator corresponds to x of n and the the numerator corresponds to x of n and the denominator corresponds to y of n. So corresponding to the numerator we have b1 equal to 0.4, or we can say b naught equal to 1. Then we have a1 equal to minus 0.5, then a2 equal to 0.25. Here in the numerator we have only one delay, so that we can write the input side 2 adders, and at the output side is of second order. We have 2 delays, so that we can draw 3 adders, then put the delays then the input side we have x of n, then the input and output connected together. The output side we have y of n, put the arrows, so this is the direct form one structure. Here we know that b naught equal to 1, it is not necessary to put here. Then we have b1 equal to 0.4. Now when we are coming to the output side, the negative values are to be substituted. Here the a1 equals to minus 0.5. So here you have to give plus 0.5, and here we have to give the negative of the coefficients as per the standard notation. So when we are directly using the difference equation, the coefficients we can directly give, whereas in the system function mode you have to give the negative values of the coefficients. And another thing you have to notice here is here we can see the equation is something like y of z by x of z, but during realization we have always time sequences, that is the input is always a time sequence and output is always a time sequence. So instead of y of z or x of z, you have to put here x of n and y of n, because we are realizing the structure. So here are two homeworks. Take the first equation. So first of all you have to write the coefficients corresponding to this one. So x of n, corresponding to x of n we have b naught equal to 1, then x of n minus 1, that is b1 equal to 2, then b3 equal to 3, then corresponding to a side, that is here we have a1 minus a1 equal to 2, then minus a2 we have equal to 3, like that. Now we know that we have 3 orders on both sides, the inward as well as the right side. Then draw the delays these are orders, put the arrow mark, then from the inward side we have x of n, outer side you have y of n. Now put the coefficients b naught equal to 1, since it is 1, not it is not, and b2 equal to 2, then b3 equal to 3. Here a naught is always 1, then minus a1 equal to 2. So it is 2 minus a2 equal to 3. So this will be the structure. You draw it neatly by yourself. Similarly, you do a lot of problems related to this direct form structure realization. Next, let us discuss about direct form 2 realization. From direct form 1, we can easily obtain the direct form 2 structure. Since the system is linear, the interchange of the input structure and the output structure will not affect the overall performance. So by keeping x of n and y of n as it is, let us swap the input and the output structure. Now, when we are swapping like this, we can see that the two delays are coming together. So, from this structure, it is evident that instead of two delay elements, it can be replaced with a single delay element, so that the overall delay elements will become half. So, half of the delay elements or memory locations we can save in the direct form 2 realization structure. We can merge these two delay elements to one, so that we get the final direct form 2 realization as like this. So this is the standard structure for the realization of direct 2 form. Now let us see how this can be drawn in practice. First, draw 5 parallel lines with a sufficient distance between them. And draw adders at both ends. Or the first 4 parallel lines. Then put dotted line here. Then at the center, give the delays. Now we can draw put arrow mark or a naught to the right side plus or a other a's coefficients in the reverse direction, and give the input x of n, output y of n. Now put the coefficient values. Here it is minus a1, here it is minus a2, here it is minus an minus 1, here it is minus an, here it is b naught, it is b1, B2, this is B m minus 1, this is B m. So this is the structure, standard structure of the direct form 2 realization. Here's an example based on the direct form 2 realization. So the question is given like that. So as a first step, you have to write the given difference equation is this one. Then the coefficients are, here you can see y of n minus 1 corresponds to this one. So minus a1 equal to minus 0.1. Then we have minus a2 equal to 0.72. Then here we have b0 equal to 0.7. Then we don't have x of n minus 1. So next one is b2 equal to minus 0.252. So these are the coefficients. So first of all, we can draw the input and output. Like this, we have the x of n and the output y of n. So in the given difference equation, the maximum number of delays are 2. So at the center we can draw 2 delays. Set inverse. Then we have the second delay. Now we can put the arrows here. Then we know that a1 minus a1 equal to 0.1. So this can be, after one delay we can draw here. Now that value equal to minus 0.1 minus 0.1. Then we have a2 equal to 0.72. That is after the 2 delay we have coefficient 0.72. Then when coming to the right side, x of n corresponding to x of n, that is b0 equal to 0.7. So this is the 0.7 is a0 always equal to 1. Then we don't have x of n minus 1. So the x of n minus 2, after second delay we have the output. So that we can draw like this. And here we have the value b2 coefficient as minus 0.252. So this is the direct form realization of the given equation. Same thing you can try for the system function. So that you have to determine the z transform on both sides, then obtain h of z equal to y of z by x of z. In that case, you have to appropriately choose the coefficients. You can see this is the final answer. So here you have two homeworks. The first case you have to put it in the standard form, that is y of n equal to minus y of n minus 1 plus 4 y of n minus 3 plus x of n plus 3 x of n minus 2. Then you can write down the coefficients, that is minus a1 equal to minus 1. Then there is no n minus 2. Next one is minus a3 which is equal to 4. Then we have b0 equal to 1. Then we have b2 equal to 3. So in this case the number of delays are 3. So first we can draw the input and output adders x of n, y of n, then give 3 delay elements. Like this. Here we have the minus a1 coefficient as minus 1. Then we have the a3. We don't have the a2 coefficient. So we can write this one as the minus a3 equal to 4. Then coming to the right side we have x of n, that is b naught equal to 1 itself. Then we have after 2 delays, that is after 2 delays we have b2 which is equal to 3. So this will be the realization, second order realization. Now the same thing we can do by the system function.